Yeah, really, there's no bad movies. I mean, people just go in with unrealistic expectations.
That's pretty bad, though.
I mean, if you go into a movie and you just figure, oh, this is going to be an hour and a half or 2 hours of my life with explosions, like the Transformers movies, things like that. And you're holding it to this unreal, like, oh, the cinema, the storyline had holes in it or something. You got those YouTube videos, the everything wrong with the latest Transformers movies.
Those were kind of bad.
They're fine. You got robots and explosions. What else do you want for 2 hours of entertainment?
Not for another 2 movies of the same thing.
Yeah, it's the same thing. It's awesome.
One of those videos did point out to me something I thought was really funny in Django Unchained. Someone gets shot and they go, instead of getting shot back, they get shot from the sides. They get shot.
Oh, I see. Well, but see, that's a little bit different. So a movie like that, now that's got to have some cinematic stuff and good storyline, because you can't just say, okay, it's explosions and things like that, because really that movie's about something completely different. You can't make a similar comment to what I made for that one. Yeah, it's always a good 2 hours just sitting there watching them whip people. That doesn't work. So yeah, I mean, the same thing with any of the Marvel movies. People to sit there and overanalyze it. It's superheroes. It's explosions. It's awesome. You're not looking for this deep, life-changing storyline. I just don't get it. All right. So let's start looking at our variable environment. So as a starting point, so now we're actually getting into writing a language, the first parts of it. And when we think about, we go back to Littman 101 class, right? How do human beings solve problems? How do we solve problems? We use our memory, we ask questions, and we have repetition. Right? Somebody want to hit the third button down if there's glare on that guy? Thank you. All right, so when we think about memory, what are we talking about? Variables. Mm-hmm. So I've made a claim that all programming languages, 100% of programming languages, will have facilities for these 3 things. All right, so I challenge you to find me a programming language that doesn't have facilities for one of those things. And then I will tell you that's not a programming language. All right, but if you want to make a challenge against this, I'm happy to have that debate. That should be fun. But in any case, when we're writing software or when we're solving problems in real life, we have to remember things. So we do that through a variable. What's a variable? Remember, back to 150. We have to understand the problem we're solving before we can solve it.
Computer science is problem solving.
That's right. I mean, the thing is it sounds boring, but these are all true things. Okay, these are the little tiny Legos that your entire computer science theoretical knowledge is built on top of. So we talk about variables. What's a variable? If you had to concisely define what a variable is, what would you say? Okay. So name, value pair.
Yeah.
Okay. Where name is the name of a location, and value is the value associated with that name. Right? Okay. So, variable is a name value pair. Now, when we have a computer program, how many variables do we have? When you write a program, what's the minimum number of variables you might have? 0. What's the most number of variables you might have? A lot. All right. All right. I rounded down, right? I rounded down. So really what we need is a collection of name value pairs. This is equal to a variable scope. Now, initially, we're just going to look at variables at the high level. We're not going to look at scope where we have, more local versions of a variable with the same name. We will. Okay, but initially, we want to think about, I'm writing a programming language. My language needs to support variables because, well, I need to support all three of those things, right? Memory, asking questions, and repetition. But let's start with variables. I have to be able to remember things. I need to be able to say, here's a name, A, and I want to set it equal to 5. And I might ask you for that value later on. So I need to store that somewhere. I need to have a facility for storing those variables somehow. All right. So now your book, what did I have you go through? 2.1 blah blah to blah blah?
It was 2.2 section, right? Because we did 2.1 with big numbers last week.
All right. So we're talking about representation. Here, the environment interface. All right. So here is our grammar for an environment. All right, so we have this constructor for an empty environment, right? So let's just go in here and just blow away all this stuff. Unimportant, right? Okay, so we're going to define EmptyEnv to be a lambda that takes no parameters and boils down to, what are they defined as, the empty list?
Yeah.
All right, so this is emptiness, nothingness. All right, do they have a better grammar than that somewhere? Yeah, this will be fine. This is an environment expression. So we have an empty environment where they haven't necessarily defined the empty environment, but let's just call it an empty list. We'll call that good enough. Then we're going to have an extended environment where we have an identifier, we have a value, and then we have another environment expression. Okay? So remember, I mentioned a few minutes ago that we're not going to start off by implementing scopes. So we're implementing the way to add variables to an environment, and I promise you the first time we do this, it won't be the best way. It's just going to be a way. All right, so we're going to define something called an extended environment or an extend environment that allows us to take a baseline environment and extend it with a name value pair. All right, so define ExtendEnv to be a lambda that takes in a name, a value, and an existing env. And this guy will produce a list containing name, value, and that env. That's what an ExtendEnv is. Make sense? Mm-hmm. So now what I should be able to do is I should be able to do something like ExtendEnv A5 empty env. Actually, let me just do a quick define. Define the env. Leave it like this. No, actually, I'm going to want that. Define the env to be empty env. And then, just so we can kind of look at these things, I'm going to do a set bang. Have we done set bang in here?
No.
All right. The env to be equal to that. And this is going to be the env. Okay, and then we'll do a set bang, and we'll do a b is equal to 7. Like that. And then we'll just print out the env.
So what does set bang do?
I'm about to tell you.
Okay.
Oh, sorry. These are symbols, not variable names. All right, so here's our list that contains a name value pair, followed by an environment, which contains a name value pair, followed by an environment, which is the empty environment. Make sense? So what does setBang do? SetBang updates a local variable This is a local scheme variable. This isn't something we're writing, but this allows us to update the definition of a local variable. So we defined a local variable called the ENV, started off as the empty environment, and then we're just going to update the value of it here. We're actually not going to use setBang very often. I'm just using it real quick for this just so we can have kind of a couple of starter environments here. So we're going to say the ENV is now equal to ExtendEnv A5 the ENV. This is no different than saying int A equals 7 and then saying A equals 9. Make sense? All right. So, and it just so happens that the setBang function boils down to a value, which is either the new value of the ENV or void if we don't use it for anything. Well, actually, in this case, it actually boils down to void. Always. So if we're doing that inside of our program, we would have to suppress that in some way unless we wanted our output of our program to have voids all over the place. But don't worry about don't worry about that right now because it's not something you're going to use very often. And I'd encourage you not to use setbangs in your code. This is just a quick introduction thing to it in case you want to update a local variable for some reason. Most of what we're going to be doing for a while is going to be passing evolving environments around because one of the things we're building initially here is this thing called an environment passing interpreter. So at any point in time when we're executing a statement inside of our interpreter based on our language, we will be executing it within the context of whatever the current version of the environment is. All right. So that's our ENV. Actually, we'll leave it like that for right now. All right. So then we have this thing called ApplyEnv. Yeah, so they gave an example here of how to create your, a crazy environment. So this is an environment where D is equal to 6, Y is equal to 8, X is equal to 7, Y is equal to 14. It's built on top of the foundation of an empty environment. All right. But we have a function here called ApplyEnvironment, and what ApplyEnvironment says is give me the value of a variable. Resolve the variable A in my environment. Okay, so we can say define apply env, and this guy will be a lambda that's going to take in a name and an environment to search within, right? And we're looking for a variable named name in env. Okay, now env comes in a couple of different forms. It comes in the form of an empty environment and it comes in the form of an ExtendEnv. An empty environment is the empty list. So if we're out of places to look and we haven't returned yet, let's just boil down to false. Didn't find it when I tried to apply it. We can decide to return something other than false, but let's just say that's good enough. Otherwise, I know I have an environment. And what does this environment look like? It looks like this. The car will be a name. The catter will be a value. And the CADDR will be an environment. So we'll ask the question, if let's just EQ for symbols. EQ name and the car of ENV, if those guys are equal to each other, and actually this is not an if because I'm inside of a cond. Okay, if those guys are equal to each other, then what am I going to do? I'm going to boil down to the catter of ENV, and I'm done. The catter would be the 7. The car of the cooter. So if the car is the name, is the variable name I'm looking for, then my answer is the value associated with that. That's what ApplyEnv does. Else, I'm going to call ApplyEnv, passing it the same name, and passing it the car of the cooter env. So I'll pass it the next level of my environment to check. That make sense? All right, so I should be able to say things like apply ENV A, the ENV, and that should give me a 5. I should be able to apply ENV B, and that should give me a 7. And I should be able to apply, let's say, a Z, and that should give me a false. That makes sense? All right, so this is an approach to a variable environment. Not a very good approach, okay? But an approach. It allows us to build up an environment. For as soon as we hit a variable, so we kind of start with something. We start with this little tiny mound of dirt called the empty list. This is the EmptyEnv. It's not even a mound of dirt, it's a mound of nothingness. All right, so that's kind of what we're building on top of. And then as soon as we define one variable, build it on top of that. Oh, you want to define another variable? No problem, we'll build it on top of that. Then we'll build it on top of that. So we get this kind of inflated environment. But it's an environment that was structurally easy to build, right? What we just did here is really no different than bin tree. Right? We gave ourselves a couple of constructors. This is what an empty environment means in our world. This is what an ExtendEnv means in our world. This is what ApplyEnv does. It says resolve this variable name within this environment. Doesn't that sound what programming languages do? If I have a variable and I want its value, it needs to resolve to its value. And where do I do that? I look in the local scope, I look in the local environment, and magically it happens. I either get a value or I get a compile or runtime error, depending if I'm on a interpreted or a compiled language, saying I didn't find what you were looking for. Okay. The book does have this thing called data structures, which I typically avoid. I typically use, and this isn't an example of it yet, but this just happened to remind me of it. We'll see if it does it, but it's built into Dr. Scheme because Dr. Scheme is kind of closely mirrored with the book, but I don't use their data structure thing. I prefer the lists. It's just more fun. It's identical. There's not a difference. They just try to make a couple of less parentheses at the cost of, I think, making things less understandable. So it's okay. So here's our empty environment. Okay, now they're technically doing this where they're giving you the word EmptyEnv as your last thing. So we're asking against null. They're asking against EmptyEnv. Fine. ExtendEnv, they're creating a list out of the word ExtendEnv and then a var val environment. That's fine. We didn't write ours like that. We wrote ours to not have these descriptive terms in there, but instead just be what they are. An empty environment is the empty environment. An ExtendEnv is a name value pair followed by an environment. So pick your poison, but we did differentiate ourselves a little bit from these two. Anybody have any questions about what we did? We just aren't putting strings in there. So we ask if it's the empty environment, we ask if it's null, as opposed to ask if it's EQV EmptyEnv. The car of it, EmptyEnv. Okay, ApplyEnv. Oh, we even wrote ours different there for that, right? We passed in the search variable, then the environment. So, all right. So it takes two parameters still. We just passed them in the other order. We asked pretty much the same questions, right? And this is kind of their report no binding found search var. So this is a error message, EOPL error, blah blah blah. We just returned false. We're going to say that's okay. Okay, so, book gives us some examples, but I typically like to write the stuff so we can explain while we're going through why we're doing something. All right, so this is the books. They decide here's how we're going to report no binding found. That means there was not a name value pair a variable was not bound to a value, the variable we're searching for. So this is just a lambda that happens to use this built-in function that came with, that's part of the book. This is Dr. Rackett's association with the book, so I usually tend to avoid that. That way, if you're using a different scheme interpreter, your code won't break. Because I promise you, if you use Bob's scheme interpreter, it's not going to have an EOPL. What does EOPL stand for?
Error programming.
No? What's the name of your book? Essentials of Programming Languages. So this is a library specifically made for your exact textbook. Make sense? So only if you're using the interpreter Dr. Scheme that was built in terms of your textbook. Remember day one of class or whatever, we had to choose our language, whatever. So if you're using a different scheme interpreter, like you're using a different one because you're doing it inside of a Chromebook, right? So her code would break. She doesn't have an EOPL unless she found some open source version of a scheme interpreter that would run inside of a web page that happened to support that. Doesn't matter. We don't care about the stupid error messages. We can just return a false, or if we really wanted to, we can return the string no binding found. That was a life-changing type thing for us. That makes sense? Not an important part of the language here.
Curiosity, are we able to, like, in some, like Python, for example, you have the %d and include string, like, values and strings, can you do those? Or do you just concatenate?
Well, kind of neither. You'd have to build your own thing because concatenation stops sort of making sense with list-based things, but you could pull it off. I mean, you can make your own. There's probably actually a built-in concat function that would take two strings and glue them together, would be my guess. But anything that's not there, we could build. But in general, I would always make the assumption that there's a lot of stuff that's not going to be built in for you just because that's the point of using Scheme. Because remember, this class is not a class about Scheme. This is not a class about a functional language. We just happen to be using, this class is about building programming languages and understanding how programming languages are innately created. And we happen to be choosing kind of like the simplest possible tool we can find that allows us to accomplish that. Like a really cheap set of Legos that doesn't have all the shapes that we wish it had. That we can build the things out of at a really kind of granular level. Does that make sense? Okay. The reason Scheme is frustrating for a lot of us is because it's very different than procedural and object-oriented languages that we've previously been exposed to. It's frustrating in its simplicity. All right. So these are just stupid error functions, whatever. So our ApplyEnv is the same, right? If we're in empty environment, we return false, didn't find it. Otherwise, if the car of it is the dude we're looking for, actually this guy makes it way worse, right? It says if I'm looking at an extended environment, then let's create a let and get the variable that we're the variable name, the variable value, and the environment. If the name matches the name we're searching for, then return the value. Otherwise, apply EnV on the environment and the environment and the variable we're looking for. This is a really long-winded way of saying exactly what we wrote here. Make sense?
It just saves those variables locally if you need them for something else for some reason.
Correct, but in ApplyEnv, we really wouldn't.
Right.
Yeah. At least not at this point. But we accomplished the same thing here. They're just being a little bit more verbose in terms of looking at the label for EmptyEnv versus the label for ExtendEnv. Nothing wrong with it. Just we didn't write it that way. Okay. Oh yeah, so here, invent 3 different representations of the invariable environment, blah, blah, blah. We're not going to do that. Error message, who cares? All right, we want to give it a EmptyEnv. What is their A list? Whatever. Let's just ignore that. It's unimportant.
What was the exercise 2.5? 2.5. At the
Oh, this one?
Yeah.
Yeah, unimportant.
Okay.
For what we're trying to get to. All right, so now this is kind of interesting. Well, they have one thing. One of those questions asked you to create a define empty ENV question mark a predicate for this. They called it an observer. And this guy's going to be a lambda that takes in an environment as a parameter. And if it's we're just going to return null ENV. That'll return true if it's the empty environment and false otherwise. Okay. Whatever. That's a little test for that guy. And then what we can do is if we really want to, we could have written that in here. Oh, did I not copy it? So now it maybe reads a little bit cleaner or something like that. But they're synonymous, right? Okay. But now this guy might be interesting. So this guy says, what if we want to extend the environment with multiple inputs? So I want to set an A, B, and a C equal to some values. So this guy takes in a list of variable names and a list of values and ultimately boils down to an extended ENV with those guys in it. That make sense? So if I want to define more than one variable at once, so we'll say define extend ENV star, and this guy is a lambda that's going to take in a list of names, a list of values, and an environment. All right, now we can make the assumption that list of names and list of values are both going to be the same. This is kind of a old school parallels array solution. So if you want to define three variables, A, B, and C, you're going to have a 3 list of variable names and a 3 list of variable values, of associated values. So we're really asking the question, we know we're done as soon as either one of these guys are out of things, right? So we can ask the question. We can say, if null low names, if we're out of stuff in low names, that means we have nothing else to do. So what will we return? Just return the environment. Otherwise, we will call ExtendEnv star on the cdr of low names, the cdr of low names, low values, and I know I have missing the S on lanes, and then an extend ENV, normal extend ENV. We're extending it by one variable name, passing it the car of low names, the car of low values, and the current environment.
There's no. Do you need a question mark for the no or no?
For who? This? Probably.
Okay,
that how you ask no?
Values, we're missing an S.
Where? Oh, here. So he's always who's in charge of my spelling?
B.
No, Blaine.
All right. So for adding multiple things, we're going to whittle down these two guys. As soon as we're out of it, then we'll just return our final environment that we built up. Otherwise, we'll call ExtendEnv star, passing it everything but the first element of names and values, as well as an updated environment, the ExtendEnv of the first name that we're trying to create, along with its corresponding value, and then whatever environment we had just a second ago. That make sense? So now I should be able to come down here, and I should be able to call ExtendEnv star, passing it A, B, C, and 1, 2, 3 in the EnV. And this should give me a extended environment with those things in it. All right, that makes sense? So this is a convenience function, it's syntactic sugar, for us to define more than one variable at once in our variable environment. ApplyEnv doesn't need to be changed because it's walking through this variable environment just like it walked through the environment before. Correct? Nothing's changed with that guy. All right, not important for us. Okay, so that's pretty much what we wrote before. Fine, okay, good. So this is where you read up to, right?
Yep.
All right, so would you agree that right now I have a working variable environment? I can define variables, store those variables inside of an environment, and if I want to get the value of a variable, I can do that. We believe, especially since I told you this isn't the best way of writing it, that we're probably at some point going to bump into some issues with this variable environment, and that one of those questions that we kind of blew past talked about having you come up with a couple of alternative ways of having a variable environment. You know, couldn't we just have a list of name value pairs? A list of two lists? Probably be just as good as what we have now. And just a little foreshadowing there, doing something like that allows us to have a more local scope. So we can call a scope a list of two lists. And then if we have a more local scope, like we're defining a function, we can push onto the stack that is our stack of scopes, the most local scope, which is the list of two lists associated with the current function. So a little foreshadowing where we're going there. Because variables always resolve to their most local definition, right? Heard me say that before in other classes? Well, the same thing's true here, but nothing keeps me from having more than one variable with the same name defined in here. I can come down here and say A is actually equal to 7. And now I actually have two definitions of A in my environment, with the most recent one, which may not necessarily be in a different scope. This might just be a bad programmer, right? The most recent one having a different value than maybe I intended. Make some sense? So real quickly, we can start seeing a little weakness with this guy. But that's okay. He's good enough for us for right now. Allows us to, we can with confidence say, yeah, as long as you play by the rules, we can store name value pairs. Okay. So now we'll go on to what's the next thing we need to be able to do. How do human beings solve problems? Memory through variables. Asking questions through if statements. Repetition is through loops and functions, let's say. All right. Now, when we say, if we talk about like a language like Java or C++ or whatever, we call it an if statement or a for statement or a while statement. These are all statements. And they fall into some different categories, but we have this idea of a lambda calculus expression. All right? And we've already been dealing with lambdas. What's a lambda? Unnamed function. Okay, so we have this language of lambda calculus, which makes us sound really smart. somebody says, hey, what did you do in class today? So, oh, we just did a little lambda calculus. I went to lunch. Had to, come down off that high, right? Okay, so so what's a lambda calculus expression? Well, it can either be just an identifier. Now, if you're in a normal programming language and you just see an identifier like A or B, what is that guy? Variable, right? And what do we do with variables? Well, that's what they do. When we see a variable in the wild? What do we do?
Power and fear.
Well, we look under the hood. We apply it. We resolve it, right? So this guy probably called it, what do they call it? A var expression. So we're going to say, hey, I ran into a variable. What do I do with it? I give you the value. How do we give you the value? I call apply expression or apply environment, whatever we called it. All right. Next kind, we have this thing called a lambda. Well, you just told us a lambda is an unnamed function. Well, what does a lambda take? Well, in our simple starter language here, our lambdas are are limited to exactly one parameter. No more, no less. If you're going to write a function, it better take something. And it better not take more than one something. All right, super simple lambda, but so now our language, our new programming language we're writing here, it knows how to support variable resolution. It allows us to support functions that are associated with a single parameter and the body of that function being a lambda calculus expression. It also allows us to support a list containing a lambda calculus expression and another lambda calculus expression. And we start thinking how this guy might work. Well, this is maybe a function that we want to apply to these inputs. So maybe this is the function add, and we're applying it to the function plus, which is being applied to 1 and 2, which our current language wouldn't support because we only get one input. But that's the, I think they're probably calling that an app expression. Yeah. Where we apply a function to its parameter is the idea. Singular, okay? Does that make sense, what we're accomplishing there? So if I have this language of those expressions, I'll go ahead and give myself this just so we don't have set bangs. And we'll just give ourselves 1A. All right, so we have an environment there that we might start off working with so we can test some things, right? All right, so we're going to create some constructors. So again, we're seeing this pattern here of working with a grammar, right? We have a grammar. This guy's called a grammar. This grammar has 3 productions. This is the first production. This is the second production. This is the third production. What can we do with productions? We can create constructors for those productions. All right, so I can define a var expression to be a lambda that takes a symbol as a parameter. And what does this guy do? He boils down to that symbol. That's what a var expression is. I can create a, what is the next one? Lambda expression. I can create a lambda, define a lambda exp to be a lambda that takes in, now a lambda exp takes in 2 parameters, right? It takes in a parameter. Okay, so probably a symbol is, I'm guessing, the definition for this guy. Just an identifier, yep. So this guy's going to take in a symbol, and he's going to take in a LC expression, or it can be any of our guys. And I think, isn't that what it probably defined it as? Yeah, took it as an LC expression. And what is this guy going to do? It's going to give us a list containing the word lambda as the first element, because we have to be able to kind of flag it as this guy as a lambda expression. And then it's going to give us the symbol as the next guy. And does it want to do it as a list? Yeah, it does it as a list. So we'll create a list out of that symbol, you know, so it looks like parameters, right? Plus it makes it extra difficult to get at it. Right? Okay, so it's a list containing that symbol. And then we're going to have our last lambda calculus expression. Okay, so that's our constructor for that guy. The next one is a define app expression. This is going to be a lambda that's going to take an LC expression 1 and an LC expression 2. And this guy will return a list containing LC expression 1 and an LC expression 2. That's what an app expression is. Okay, so if we were building these things up, these are our constructors for making those things. Now, keep in mind, this doesn't necessarily tell us what to do with them. It just tells us how to build them. This allows us to conveniently build different types of expressions. All right. Then we have predicates for these guys. So we can have a predicate for each of these. So predicate for var expression, just put it right underneath it. This guy is just going to be, he's going to be a lambda that takes a LC expression as a parameter, and he's going to return whether that guy is just a symbol. That's what a var expression is, right? If you handed me a lambda calculus expression, and I look at it, I say, are you a symbol? And I return my answer, that tests for being a var expression. All right. Now, again, if we are, so let's do define lambda exp. This guy will be a lambda that takes a lambda calculus expression as a parameter. Now, we can be safe here, and we can say, well, if it's not even a list, we want to return false, right? So we can say if null LCEXP, then this dude is definitely not a lambda calculus expression. Otherwise, return EQV car LCEXP and lambda. It's either not even a list, which means it's definitely not a lambda expression, or it's car as lambda. Actually, we need to do a couple of things here. So we could say, or because this says, are you an empty list? So we're going to say if not list LC expression, or you're the empty list. If one of those two things is true. If you're either not a list at all, or you're the empty list, then return false. Otherwise, return whether or not your car is lambda. That makes you a lambda expression. Make sense? Last one, app expression. This guy will return a lambda. That is an LC taking an LC expression, and he's going to check to see if it's a list containing two elements, each of those being a lambda calculus expression. Right now, we don't have a test specifically for that. Lambda calculus expression means it's one of our three kinds of things. So for right now, we would say that this guy is a, will return list LC exp and length. Let's see, and equal length LC exp 2. Call that good enough? So this says, look, if you gave me a list and there's two elements in that list, for right now, we'll assume those two elements must be lambda calculus expressions because that's our world we live in right now. The book might have gone about this a little different, but that's okay. Then that's what this should boil down to. All right, so we have predicates for these guys. All right. So we already did this. Okay, so for next class, we're going to read some more. Read from 2.3 to 2.5, not including 2.5. So all of 2.3 and all of 2.4. Okay, because the next thing we're going to be looking at is something called occurs free and occurs bound, which allows us to ask whether or not a variable is defined by a definition or if it's just there. So whether or not a variable is lookupable in the current environment or if it must be either from something more global or it's made up. All right, so we're going to be looking at processing lambda expressions. I will, as a starting point, if you want to kind of work through, look at this code, I'll put this code up on Slack as a starting point. It does deviate from the book probably a little bit, but that's okay. And I will see everybody on Wednesday. What's up?
Can you stop the recording?
Yeah. But then you have to wait for me to upload it real quick.